Hello students and welcome to our chemistry lesson. So today we're going to look at an electrochemical cell. So by the end of the lesson we should be able to draw an electrochemical cell and be in a position to explain how it works. So what is an electrochemical cell? So an electrochemical cell is a device that is used to convert chemical energy into electrical energy. Specifically in this cell, it uses the concept that we've been looking at, that is the oxidation and reduction. And that's why in most cases it's also referred to as the voltaic cell or the galvanic cell. So basically, if you pick a metal, for instance, if you pick zinc metal and dip it in a solution that contains zinc ions, for instance, here I have a zinc sulfate solution, then the metal, the atoms on the metal surface, so the atoms on this surface which are into contact with the solution, they normally tend to lose electrons. So they tend to lose electrons, and so they go into solution. But those those electrons that are lost, they tend to remain on the surface of the metal rod, while the ions which are formed goes into solution. In this case, our ions, of course, they are the zinc ions, and so we have something like that. So this is what we are talking about. We have the zinc. It is losing electrons, and in the process, it is going into solution, and so we have something like that. So with time, due to the accumulation of the negative charges on the metal surface, they tend to attract back the positively charged ions. So this reaction also takes place. So we have the zinc ions which are in solution. So these are the zinc ions there. They are attracted back by the negatively charged. We know opposite charges attract. So they are attracted by the electrons, the negatively charged electrons, and once they are attracted, they form the zinc solid. So we have two equations that are taking place in opposite directions. So from our reversible reactions, so we have seen that we're going to have both the forward reaction and the backward reaction. So at a certain time, these two reactions will achieve the state of equilibrium. They will achieve the state of equilibrium, such that the forward reaction and the backward reaction are taking place at the same rate. And when that happens, then we're going to have what we call as the potential difference. So when you separate opposite charges, here we have the positive charges and here we have the negative charges. They are separated. So when you separate oppositely charged charges, then we normally develop what we call the potential difference. So when you dip a metal into its solution, then it normally develops the potential difference. It is possible to calculate the concentration of the electrons on the metal surface, and the units used to measure the concentration of those electrons is referred to as the electrode potential. So we have this. So this is basically such a setup in the electrochemical cell. We normally refer to it as a half cell. And this is how we represent a half cell. A half cell is represented by, on one face we have the metal, which is separated by a stroke. Then we have the metal ion. So specifically for our example here, if I want to represent a half cell for the zinc, then I'm going to have zinc stroke, then the zinc ion. So have that. So what does this represent? This represents the interface, or the interface boundary between where the potential difference is experienced. So different metals have different ability to form ions, to ionize. So there are some metals that will ionize very fast, while others will not ionize as fast as others. So that makes it impossible for us to measure the electrode potential of one half cell. So if we want to measure the electrode potential, then we must have two half cells. We must connect two half cells. So I'm going to connect two half cells, and then from there we can be able to measure the electrode potential difference of the two half cells. So for instance, I can have one half cell there, whereby I am using zinc electrode. So this is zinc electrode, and then this is zinc sulfate. Then I also have another half cell here, but this time round I use a different metal. So I'm going to use, in this case, I'm going to use copper metal, and then the solution, copper metal dipped in copper sulfate solution. So to connect the two half cells, then I'll need to connect them using a wire, and at some point here I'll ensure I have a voltmeter. Then I connect them like that. But if you're very keen, you can see that's not a complete cell, because there is no connection. The current is not complete. It's not a complete circuit. So we normally connect the two solutions using what we call as the salt bridge. So the salt bridge connects the two solutions. As you can see, the salt bridge does not touch the electrode. So a salt bridge is basically a substance like a filter paper immersed in a saturated solution of the most common solutions used are we have the potassium nitrate and or the sodium nitrate. So, however, the kind of electrolyte or solution used, you must ensure that that solution will not affect or will not react with either this half cell or the other half cell. It will not react with the zinc sulfate or the copper sulfate. So the function of the salt bridge is to complete the circuit. Now you can see our circuit is complete, and once the circuit is complete, then the electrons, remember we saw that each half cell will ionize, and some negative charges will form on its surface. So the electrode with the highest concentration of the negative charges, then the electrons will flow from that electrode to the one that has less concentration. So like for instance, this is just an example. Yeah, so the electrons, if zinc has the highest concentration, they will flow from zinc to the copper. And as that happens, then our voltmeter here will record for us the difference in the electrode potential of the two half cell, a measure which is known as the electromotive force, all times denoted as the EMF. Yeah, so basically that's how our electrochemical cell looks like. So in our next part, we're going to look a little bit on the salt bridge, and then we'll proceed on from there. Thank you.